All right, so today we are going to talk about the third lecture on memory hierarchy. We are going to talk about cache misses and their remedies. And today we are going to talk about the software version because actually as a programmer, there are lots of things that you can do. But again, I know you have been so tired about the slide, but I do want to mention that again, right? So every time when you execute your program, every instructions come from the memory. Every piece of data, they all come from the memory. And the memory, by default, they are so slow in a way that the affordable technology only give you 100 to 1,000 times lower latency than your processor speed, which means that if we don't do anything with it, there's nothing, it's very meaningless to get performance out from your computer. So it turns out our solution is that we build multiple layers of SRAM as a memory hierarchy. And the good thing is that because your code has locality, so as long as you design, architect your cache in a way that the locality can easily be captured, it's easy for you to get high hit rate. And with that high hit rate, we are going to capture most of the memory access within the small but fast cache. And then seldom you will need to visit the DRAM. So you will see like very minor difference. So it's pretty much like, you know, we could have built everything in Los Angeles, but we still built like a county office. We still set up some of the, like we set out a DMV nearby, right? So you don't have to drive to Los Angeles just for a driving test, behind a wheel test, right? So this kind of concept, and computer does it. And so to capture the locality was good with efficient access time, efficient structure. Turns out the solution that we are using today, no matter it's for instruction cache or data cache, it's all way associativity cache. In a way that in a cache, we organize cache blocks. And the reason why we want cache blocks is because we want to capture spatial locality. So each time when you have a cache miss, we just bring in fixed chunks, fixed size chunks of data into the cache. And for those fixed size of chunk of data, we don't allow them to go anywhere in the cache. Instead, we map them into sets. So by mapping them into sets, you get an effect as a hash. So people know the good thing about a hash is that the search time is older one, right? So, but how do I determine where the data block should be going, or where should I look for a data block? So the answer is that you have to look over your address. And in your memory address, based on the concept of cache, because we have fixed size chunk, so the last significant bits, least significant bits, will be used as the block offset. And depending on how many bytes are there in your block, you will need corresponding number of bits to provide an address for them. So that's the idea of weight associativity hash, and the block offset. And as we said, the idea of set is pretty much like a hash function, and our hash function is pretty simple. Depending on how many sets do you have, we number them, we label them in order. So here what we do is that, okay, if you have a certain number of sets, we just log the number of the sets by 2 in a way that that's the number of bits that you need to address all the sets you have. So for this figure, we have 8 sets. So that's why we need 3 bits as the set index. And the remaining part, because every byte in the block would have the same prefix in their memory address. So that could be used as an identifier to see if this block contains the data that I want. So it turns out the search process will be pretty much like, first of all, you partition the address into 3 different parts: tag, index, and offset. And then use the block offset. You identify how many bytes within, or where are the bytes within the block you should output as the return of your access, and then or where you should update your data, right? And then use the set index. You identify which set of blocks may contain the data you want. So it turns out we figure out for this example it's 10, so it's the number 2 set. So, and then we compare the tag. If any of them is matching the 1, and typically it should only be 1, and matching the one that you are searching for, that's a hit. Otherwise, it's a miss. So that's how we end up with the search process. And you are really annoying how many bits, how many in each field. So here is why we have this C equal to ABS. By using the capacity, using the associativity, by using the number of the block size, these 3 are typically known when you are on top of a processor. As I show you, the command would tell you this, right? And then also another thing that is known is the number of bits in your memory address, which is given by the processor architecture. So you can safely assume every processor right now you are using is a 64-bit address. And then using C equal to ABS, you are going to get S, and use log B log S. You are going to get the block offsets and number of bits in the set index, and then the remaining bits will be used as tag. So in this way, you know how to partition your memory address, and then that's how you get how you can use that information to simulate the behavior of your code on the cache. So with that, another thing important is that how we perform memory access on our processors after we have this memory hierarchy. So the basic idea is that, again, depending on you are doing a read or a write. So for this example, it's a write. And I got a memory address, partition it into tag, index, and offset, and see if the indexed set contain a block with the same tag. If that exists, I know it's a hit. And if it's a write, what you need to do is that you have to update the word that you are acting on with the incoming content at the location of your block offset, and set a dirty bit so that we know it's been modified. And then once you modify at this level, it's okay for you to return. However, if it's a miss, you have to find a victim block, and typically use policies like LRU. And I'm not a big fan of talking about these policies because I think they are boring. And the thing is, After you find out the block that I want to kick out from the same set, I have to examine if this block is a dirty block or not. If it's a dirty block, but you don't present it or update it somewhere else, the consequences is that you are going to lose that data forever. So if you find the block that you are going to replace is the dirty one, you have to write it back to a lower level memory hierarchy. However, and then you can ask the lower level memory hierarchy to give you the block that you want. However, it's also possible it's still a miss in the lower level memory hierarchy. So it turns out what you need to do is, again, find a victim block and see if it's dirty. If it's dirty, write it back, and then fetch the block from the lower level memory hierarchy. And gradually, you are getting the block and perform the update in L1. So that's the whole process. So with that, you should be able to simulate the behavior of your code on a given architecture. But today, I want to teach you as a programmer, how do I optimize my code? And to know how to optimize the code or what kind of technique that you should take to optimize your code, it's really important for you to figure out what's the source of cache misses in your code. So today, we are going to first talking about the taxonomy of and reasons of your cache misses. So if you have done a reading, there are 3 types of misses, which we call 3 Cs. The first one is called compulsory miss. So maybe I can ask you a question. What's your name?
Albert.
Albert. Okay. Do you know what is NUMA architecture? You know? Okay, fine. Do you know what is NUMA architecture? Right? So here's the thing. Is this the first time you hear that term? NUMA architecture? You have heard it before? What?
Newman?
No, NUMA.
No.
Okay, right? You never heard it before, so you don't know it, right? So that's called compulsory miss. So anything, the first time, any block, the program first touching it, it's considered as a compulsory miss. And it's reasonable kind of miss, right? Because if you never touch it, you're going to miss it for sure. So that's compulsory miss. And it's also called cold start miss. That's probably the easiest type of miss that you can understand. And the second type of miss is called capacity miss. So capacity means that, okay, if I don't increase the cache capacity, there's no way I can get rid of that miss. So for example, if the code is repetitively traversing a data structure that is larger than the cache capacity, there is no way you can get rid of that kind of miss. Agree? That's called capacity miss. And the third type is called conflict miss. The conflict miss means that the cache may not be full, and the block was previously presented in a cache, but for some reason, the block gets kicked out. So the next time you access it, it becomes a miss. So that's called conflict miss. So now, can you get these 3 different types of miss? Right? So for example, the first time you hear NUMA, that's a conflict, that's a compulsory miss, right? And if you get confused NUMA with, what's the other one? Newman, right? It means, well, they all sound similar, right? They all map to N set in my cache, right? And because I heard Newman, so I kick out NUMA, right? Or because I heard NUMA, I kick out Newman. That's called conflict miss. But if today I give you a lot of N's like Newton, NUMA, whatever, I cannot remember all of them. That's called capacity miss. Does that help? Okay, so not sure if that helps, but it's better to practice it. So now, given our old friend, can you tell me how many of the cache misses within this pieces of code are conflict misses? All right. After the first round of individual thinking, a lot of you think it's D, some of you think it's E. So why don't we go ahead and discuss with your friends and see if the majority gets it right. Okay, so after discussion, yes, I guess most of you would pick D. But why? Why do you guys think it's D? It's almost 100, but not 100? The beginning? Okay, a few ones maybe compulsory miss, and but the rest of them you think they are conflict miss, or so a quick math tells you it's probably E. Is that good? So definitely it's okay because this is a pop-up quiz, right? But um, and I like that kind of intuition because sometimes you need an intuition to judge if the answer you derived at the end is correct or not. And most of the time, that's good enough for a programmer, right? Because you just want to have a rough idea of what's going on there, and then you can start practicing it and changing it. But you know, to give you a full understanding about is that true or not, we still have to go through that, right? So first of all, right, we use C equal to ABS to get this information. And again, when A0, this is the address, this is the partition, you are tired about this. Now, you all know this is a miss, but what type of miss at this point? Compulsory miss. Why this is a compulsory miss? First time access, right? So for this piece of code, we never touched A0 before, right? So that's a compulsory miss. And again, you know, there's nothing to replace because we just start running it. There's nothing we are kicking out. And now the second address we are accessing is this one. And this is the tag and index. This is also a miss. What type of miss? Why this is a compulsory miss? We never accessed the array B before, right? So this must be a compulsory miss. How about, so similarly for C0, D0, you all know this is a compulsory miss. How about this one? What type of miss? So some of you say capacity miss, but is this a capacity miss? What's the total capacity of the cache? 32 kilobytes. How many blocks are we accessing for now? 4. How many space are they taking? How many space are we taking? 64 byte per block. So it's 4 times 64. Tell me, is it more than 32 kilobyte? So is it a capacity miss? It shouldn't be a capacity miss because we still have space in the cache, right? But why this is a mess? It's still the first time we access E, right? So this is still a compulsory miss. But in the meantime, we kick this guy out. Now, for this, we know this is a miss, but what type of miss? Conflict, right? Because this time we have A0 and A7 to A7 already presented in the cache, right? So it was there before. A1 was there before, together with its neighbors A0, A2, A3, A4, A5, A6, and A7. They were all there before, right? But just because you want to accommodate this E0, so I got kicked out. So what type of miss is that? Conflict miss, right? So you can probably imagine the conflict miss would keep going on until when? What? Until we when? Until we reach A8, right? So that's what's happening here, right? So 7 out of 8 are conflict misses, so that's why it's 87.5%. So now, how about our new friend, Intel Core i7? So this should be 48 kilobyte, 12 way, but that doesn't affect the answer too much. All right, so let's take a look. After the first one, okay, so some of you think it's A, some of you is E. So why don't you go ahead and discuss with your friends regarding what would be the right answer. All right, after discussion, anything change? More of you think it's A, some of you think it's E, but well, okay, so 58 to 42, 57 to 43, 55 to 45. Okay. Okay. All right. So you know it's live, right? Okay. So what the question was asking? Okay. So the thing is that again, right? Let's go through this, right? What kind of miss? Compulsory. Okay. What kind of miss? Compulsory. What kind of miss? Compulsory. What kind of miss? What kind of miss? Compulsory. What kind of miss? It's a hit. Okay, good. Okay, it's a hit. It's a hit. It's a hit. Right? Okay, let me skip to the next slide. Now, for A7, still a hit. B7, still a hit. C7, still a hit. D7, still a hit. E7, still a hit. How about this one? Compulsory miss, because that was the first time we touched anything in a block of 8, right? So what does that mean? All the misses are compulsory misses, right? What the question is asking for. How many of the cache misses are compulsory misses? You know, so a lot of times you guys were thinking about, the description is very confusing. Unfortunately, sometimes the description is indeed very clear. It's you confuse yourself, right? So it's actually 100%. All of them are compulsory misses, right? And sometimes you guys, I mean, sometimes I feel like that's a recent issue because I never had that issue before for this assignments because in the past, people are more patient because we live in a world that we are still watching YouTube. But right now, people are living in a world that people only have 20-second concentration on a video, right? That is called TikTok, right? And if you are interested about TikTok, next quarter I'm going to invite TikTok to give us a tech talk and some recruiting event. Yeah, but okay. So the thing is, sometimes spend more time reading the paragraphs before the assignment. That tells you a lot. And sometimes pay more attention to the keywords within, or everything is here for a reason, right? Because the slide is such a limited space. So I won't put a sentence that is useless. So be careful about what's being asked there. So here, everything is a compulsory miss. So that's 100%. Okay, so it seems like all of you at least get some idea about what type of miss are we having. And it's very important as a programmer, you know how to do it, right? So I want to go with a few things. So maybe, right, as a programmer, you can tell me, right? A lot of you might already know what the SQL query is doing, but if this SQL query here, the select statement, is going to select a column from a table and compute the average of that column, and that's the most frequently type of operation this database system or this application would like to do. How are you going to design your data structures? Okay, I think I get almost 30 of you voted. So a lot of you might, it's interesting. So last reading quiz, I have the survey, and some of you think I give you too much time. Some of you think I give you too little time to finish a reading quiz, but the quiz. But actually, if you check this slide, right, there's a small counter here, which I can see from my control center, and typically I would end a poll if I see like more than 75% of you answered. So that's why some people are not in the classroom, if they voted, that's actually really annoying because it's affecting my judgment. All right. All right, so after the first round, okay, some of you think it's A, some of you think it's B. So why don't you like talk with each other and see what you guys think? All right, let's see what you guys think. Ta-da. Okay, so after discussion, more of you think it's B. So why? Anyone would like to share your thoughts, especially those one who decided to go with the majority? What changes your mind? Okay.
My original thought was
Mm-hmm.
we have an object array, so arrays will always be stored kind of one after the other, and
Mm-hmm.
make it easier to access
Mm-hmm.
memory. So if we have an object that points to various arrays, that'll make it easier to work with the cache. And the opposite is an array of objects. You'll have an array that contains a lot of objects, and those objects can be stored anywhere in memory. It'd be harder to like bring as blocks.
Mm-hmm.
So I went with B as it might be faster.
Okay. Other thoughts? Okay, so the answer is object of arrays, right? So, oops. But how significant difference is that, right? A lot of you might think about, you know, I took like a data structure class or software engineering class. They tell me like the array of objects looks so fancy, so great. It's good to read, right? Agree? Yeah, right. And it's very intuitive, right? But forget about those when you are having performance issues. So here we go. So here is the code for array of objects. And so I don't know how many of you are familiar with the SQL engine, but typically what happened is that we would parse the syntax of SQL and we still generate the abstract syntax tree, and then we emit the C code to access the data that's located on your disk. So SQL is a very high-level abstraction, and in fact, SQL is kind of like a programming language in a certain way that it's pretty much like Python from my perspective, and the SQL engine is pretty much like a Python runtime. But instead of like Python runtime that generates the code natively as machine language, SQL typically they would call libraries or they would generate C code and then the C compiler runs it. So that's how SQL works. And so here's the C code that might be generated if you have array of objects in implementing this average query. And this is the code that you will generate if you have objects of arrays. So array of objects, the idea is that I treat each of the item, or say, like for example, this context is about students, right? So I would track each student as an object. And in terms of programming, I have to be really careful, right? So in terms of programming, and each object would have its own properties. For example, the homework grades, right? The ID, the name, the email, whatever, right? So when I store, I create objects, and then I have an array of objects, means that I create an array that contains these objects. That's array of objects. And for object of arrays is that it's a joined object. And the object itself contains a lot of arrays. And each of these arrays contains homeworks, regardless where is it from, right? In some order. This array may contain the IDs, but also have an order. And for the other column, it contains maybe something else, right? So that's the idea of object arrays. So of course, if you take an object-oriented class, they will tell you array of objects is the right way to go, right? That's typically what people would tell you. But let's see what the performance difference. So now here's the code that would perform the search. And now I'm going to run the code. So for array of objects here, I assume that I am searching for 2,800 students, which is pretty much the number of students in UC Riverside. And assuming that everyone is very hardworking, so everyone has 10,000 items before they graduate. And then here's the performance. So for the select query here, if you have an array of objects, which is the recommended approach by your object OOP teacher, it would take 7.6 seconds. But if you do the way that computer architecture teacher tells you, it's only 2 seconds, right? So in fact, if you do the thing that computer architecture tells you, originally you need 4 computers, but right now you only need 1 computer, so you save a lot of money. And company would like to have you stay. And in fact, recently, I heard some people from industry, they say, you know, the people who won't get hired are actually those performance programmer, which is very difficult to find. And if you know very well in computer architecture, you will be the one who can do the performance programming thing. So that's why we really want you to learn a lot from this class, because, you know, like the recent layoff tells you one thing, right? People would typically think like if you get job at Google, it's like a 10-year job, but that's not true, right? That's not true. They remind you that's not true. There's always a downturn in industry. But I also see a lot of people, they work in tech companies, high-tech companies, even though they are 70s. Because, and if you check the profile of them, they are not the ones working on the front end. They are typically the ones that are working on the infrastructure stuff, working on the back end. So if you consider computer science, computer engineering as your lifelong mission, lifelong goal, lifelong career, you probably should learn more about in the performance part. All right, but set it aside, right? The rationale is this, right? If you do array of objects, your access pattern is pretty much like I would go with one homework and go to another, right? But if you do object of arrays, all the homeworks are just within the neighboring stuff. So that's why object of arrays is more efficient. And in fact, the select statement that I show. It's actually one of the most frequently used type of statement, right? Do you agree with that? A lot of you have experience with a database system. You know I use select every day. So turns out a lot of us would think a database table like this, right? And visually, ideally, you are thinking about, okay, so this should be a row, this should be a row. Agree? However, most of the time in computer systems, we don't do this kind of row store, right? So the row store means that, okay, my record is aligned like this on disk. But actually, this is very inefficient for the select type statement. So it turns out most of the database system, they would do column store in a way that each column is stored consecutively. And however, we keep the order of, we keep the records within each column in a certain order. So you know the first one must belong to Smith, right? So that's how we maintain the database system. So question?
So in this case, if you were to flatten the 2D array, would we get better performance?
Say again?
So for this case, if we flatten the 2D array, will we get better performance?
Okay, so here's the thing, right? There is nothing called, there's nothing called 2D array in terms of memory abstraction. So that's actually the very last assignment question in your assignment 3, right? That I'm going to tell you like how 2D array is actually implemented, and in fact they are remapping the 2D array as 1D array and in a row order fashion. So if you don't reform your data structure as column ordered, you are not going to take advantage of select, performance of select. You are not going to take advantage of spatial locality when performing select statement. So most modern database systems, they do column store for this reason. And again, if today I have a different type of statement that is very frequently used, that may change your mind. But for now, because how people use database system is frequently the type of select statement as we shown before. So that's why most database systems nowadays are designed as column store, which is very content intuitive. When you generate the code, it's not really software engineering friendly, but there's a reason, because as I show you, 4 times difference. Isn't that huge? Isn't that huge, right? Like you can save the company like 75% of the electricity bill. All right, so now the second type of this group of optimization is all about loops, right? So loops are the most frequently met code structures in your when you are doing programming. So let's see. So if you guys remember, this is actually from the second lecture, right? So we have this demo, complexity, these two are totally the same. Instruction count, they are totally the same because we don't specifically specify the clock rate, so they are pretty much the same. But the CPI on the right-hand side is a lot worse than the left-hand side. And so here's the thing, right? So and if you do the left-hand side, because now you know, right? Because I traverse the, I increment J first, right? So it turns out it's a row order access, right? And that's consecutively located on your memory space. So you get better performance. And so this one, you don't have that benefit, right? So this difference between A and B, like change the loop index order. That's called loop interchange. All you need to do is to change this and this, right? And as I show you, even I turn on compiler optimization as -03, nothing changed. Compiler don't do loop interchange for you because they are not confident if doing this would change the result of your code. So that's something as a programmer you should keep in mind. But okay, now the second question is, okay, we see these pieces of code, right? And I do want to implement this algorithm on NVIDIA processor. However, if the code performance is like this, how can I deal with that, right? So now let me give you an option. How can I change the cache? If I do this, what's the new cache miss rate? Okay, look at, okay, I love this graph, so why don't you go ahead and discuss with your friend. Go. Okay, so now let's take a look. Okay, so it's concentrated in A and B, but is it A or B? You believe it's C? So why don't we just run a demo and see what's going on? Do I have the demo, to be honest? Let me see. Okay, it looks like I do. But am I on the right place? Oh no, this is loop interchange. So how about this? So this is the loop vision, and okay, if I run it on, because we recently changed the machine, and okay, let's see what's going on here. Okay, so what do I get? Nano B, nano A. Okay, so I guess the demo is not well designed. Okay, so the version B is the original version, and this is version A. And you can see there is a very significant difference in cache misses, right? So if you do things on the left-hand side, you are going to see significant drop in cache misses, right? But now the question is that what's the percentage of that? So there's a quick way of analyzing this. So for these two loops, right? Okay, regarding the total amount of cache accesses, how many portion, how big the portion the first for loop contributes? First of all, you guys agree this is equivalent to the original sample code, right? So for this, how many portion of the cache accesses is the loop going to contribute for the total pieces of the code? What? 1 out of 8? No, I'm talking about cache accesses. 4 out of what? No. Like how big the portion of total of within total number of cache misses this loop would contribute? What? 4 out of 6, right? So if you look at that, both loop has 512 iterations, And this one incurs 4, this one incurs 2, right? So the first part of the loop, okay, let me use a different color. So for this part of the loop, I contribute a total of 4 out of 6. What's the miss rate for the first for loop? 1/8, right? 1/8. Why is 1/8? Because if we modify the code as the first, like the first loop, we are only traverse 4 different data structure at the same time. So they would perfectly fit into the 4-way cache. So you are only seeing compulsory miss, right? Now, how about the second loop? We are contributing the remaining 2 out of 6. What's the cache miss rate here? 1/8? 1/16, right? Because this one is going to be in your cache, right? Because the last one we access is actually restored to E, right? So that must be the least recently used. You won't be kicked out, right? And here, when I want to accommodate DI, I do want to kick out someone, but I will pick either A, B, C to kick out, but not E. So E will be a forever hit, right? So in this case, it's only 1/16, right? So if you count this, it's actually roughly 10%. It's actually 10.4%. So that's why the answer would be A. Question? Because there's no miss in EI. Right, which I already tell you, right? Question?
Is it because the I is less than 500?
Oh yeah, one thing to memorize right here, to notice that here is 512, so it's less than the cache size. So there's no capacity miss involved here either. Question? Oh, good. Okay, so now you see like loop fission is a very efficient way to address the issue on NVIDIA processors, right? So like, okay, again, this is counterintuitive, right? Because typically as software engineer, you think, okay, if I can put everything within a single iteration, it's easier to understand. People love it. But why? Sometimes you see some embedded system, why they separate a loop into 2? Because it's more efficient for a computer, for computers, right? And that's not intuitive. And that's, again, something your compiler probably don't know how to do it, right? Okay, so now, another type, but now let's think about that, right? So if the code, like, okay, so the left-hand side is the code after loop fission, and the right-hand side is the code before loop fission. And if today you have an Intel processor, which one would be better? See, I have an Intel bottle. This is actually the old logo of Intel because I got it around like 10 years ago when I was at Intel. And it's interesting that last summer, I also worked for Intel, and the worldwide ID, which is the worker number I got, is the same as the one that I previously have. So it's actually pretty senior compared to the rest of the group. And that was funny. Yeah, I think only my manager has an worldwide ID that is smaller than mine. All right, let's wrap up. Okay, so we love to have some discussion on that. So why don't you go ahead and discuss with your friends? All right, let's wrap up in 15 seconds. Okay, I think the slide was putting, oh, it's actually right. Okay, after discussion, more of you think the answer is D, but no. Okay, what do you think?
It's E.
You think it's E. Okay, why do you think it's E?
Because I think compared to A, the only more array E
Uh-huh.
access in cache,
Mm-hmm.
but that won't take a lot of time.
That won't take a lot of time?
Yeah.
You think so?
So
Okay. Have you started your assignment 3? Okay, the assignment 3 actually tell you how slow it is, even though you have cache. But, sometimes all you need is a demo to convince you. I think I should have the demo. Here we go. Okay, so this piece of code, let's run it on Intel processor. Oh, so that's actually on Nano. Okay. Forget about that. So, boy, why am I pressing that button? Okay, stop this one. Stop this one. Okay, run the next one. Okay, so this is what you got with Intel processor. So with Intel processor, right? If I do the V version, which is let me see. Oh, okay. So I run A first and then run B. So if it's the A version, right, it actually tells you it has more memory accesses, right? And if it's B, it actually have fewer amount of memory accesses, right? And I owe you a demo for the performance. So what was that? Okay, so it's loop B, and loop A. Okay, so let's see what's the performance of that. And sometimes, right, in Jupyter Notebook, if you just want to do some interesting experiments, you can like add a cell like I do here, right? And that would give you chances to type some comments. So what I want to do here is potentially ball grind. No, I don't want to do ball grind. I just want to run loop B and also ball grind. Okay, loop A. Type. Okay. Time. Okay, see what we got. No such file in directory. No. Oh. Here we go. See? Because the code is pretty short, so you won't see that significant difference, but it's slightly faster for version A. Well, it's 0.021 versus 0.016, right? So that's 21 over 16, right? So that's how much? 5 over 16 is almost like 33% faster, right? So if you scale it up, the difference is going to be more significant. So here is the thing, right? So for, I think I flip it a little bit. But the thing is that if you do it according to the right-hand side, because you have fewer references, and in Intel processor, they are so well designed in a way that we avoid, so, like Intel is a company that works with customers closely. I'm not advertising for them, but like when I work as an engineer for Intel, I'm actually collaborating with a big database company, which I cannot tell you who is that. But we have to figure out what type of stuff that programmers in their company, what kind of code they like to write, and figure out how to design our processor accordingly. And turns out they love to write the code like the right-hand side. Okay, let's make our weight associativity higher. And a key thing is that Intel is probably the only company that can do that because they have the best process technology. And some people will argue that TSMC has good process technology as well, but I can tell you, I'm from Taiwan, so I have the authentication to talk about this. TSMC is not very honest regarding their process technology. So most of the time, they only tell. So like Intel, so for example, Intel would typically say this is like a 7 nanometer technology if like saying like 30% of the transistor can be done within that nanometer. But for TSMC, if 5% of them can be done in that nanometer, they would say it's a 7 nanometer. So that's a key difference. So it turns out it really affects the performance of your memory when you build them. So, okay, but set that aside, right? So for this piece of the code, if you are an Intel processor, B is better. So here's the thing, loop optimization of something that a compiler cannot do if they don't have the information of the processor architecture. And typically, they don't do it for you because when you compile it, most of the time, you don't pass the microarchitecture flag. And once you do that, that piece of the code is pretty much specific to a certain architecture, and then the generality has been affected. So most of the time, people, when they compile the binary, don't optimize for that. So as a programmer, it's something that you could do, and you should do. If you know most of your customers is going to run this on Intel processor, then this is what you will have to do, right? So in the good old days, right, although AMD spent a lot of time, okay, so there was a very old history. So when the time that processors start to incorporate vector instructions, then AMD and Intel has their own version. But in the end, AMD failed because their version of extensions. Programmer only choose to use the Intel ones. So they learned this. So architecture design, they made the architecture to be compatible with the existing code. So programmer doesn't want to change code. And Intel's want the programmer to change the code. So it turns out Intel get a failure and become backward compatible with the AMD solution, right? So, but one thing I want to tell you is that hardware company learned this, that programmers like you guys are so lazy to change your code. So we try our best to make the product compatible with the user behavior. However, now it's an era that there are not that many things you can do on the hardware. So it goes back to you guys, right? Like what David Patterson said in the talk, right? We have been giving you free rides for 30 years, and now it's over, right? Right? I do a citation. This is said by David Patterson, right? So when you write your programming assignment, if you copy paste from somewhere, it's better to have an assignment, a citation. But most of the time, even with that citation, it's illegal to do that. But anyway, so here's the thing for loop optimization: when to use fission, when to use fusion. That's something as a programmer, you have to judge based on what's the underlying architecture. All right. So the next is probably the most relevant to your upcoming programming assignment, called tiling. So again, let's go back to this one. Matrix multiplication. We already have this demo, right? And the answer is that it's not going to scale with your computational complexity. And why is that, right? So let's do an analysis of that. And this is an old Core 7 architecture, but it still stays the same. So let's look at the code of matrix multiplication, the very basic version of the matrix multiplication. So we start counting C00. And to count C00, you take a row and a column from A and B, right? For this row, it's the size of a single row, right? So if you have a row that is 2K elements, and if this is a double, how big the row is? 2 times 2K times, how big is a double number? How big is a double number? 8 bytes, right? So each row would actually be 2K times 8 bytes, 16 kilobytes, right? Okay, and how about each column? It's tricky, right? Because each element in a column is essentially belong to a different block, right? So if you have 2K in a row, it's actually 2K times the block size, so 2K times 64 bytes, right? Okay, so that's why I'm saying the size of L1 cache doesn't matter here, because you are going to hit capacity miss issue anyway, right? There's no way you can accommodate all of them, right? Agree? And it's probably okay when you have a small size of row, but it's going to be worse when you have a big size of the row, right? So let's take a look of another algorithm which your textbook already showed you, and we are actually asking you to practice this as your assignment, is the tiling algorithm. So here's a tiling algorithm. Oh, wow, right? It's very complex. It has a lot of loop, and it's hard to read. However, the idea of tiling algorithm, if you pay careful attention, here we divide the array size, we divide it by a certain factor called n, which means every time when I perform this inner loop, right, I only work on a small tile of matrix. So for example, instead of go all the way to the end of a row, I only access a chunk within a row or a chunk within a column. And if this row and column or say all the rows and columns that I need. So here, when I compute C, I also restrict the size of data that I would visit within the same chunk size, right? So what does that mean is that within a limited amount of time, I'm only going to work on this chunk, and this chunk. And if you program carefully, right, this sub-row, sub-column, they would all fit into your cache, right? So that's why it will work, right? So now let me give you a demo on this. And then you can know how efficient was it. So here is, what was that? Okay, so here's the matrix tiling algorithm. Indeed the same as the code that you have. And now, I think I should have the, okay, so, and this is the baseline matrix multiplication code, right? And now let me make the code. And do I have, it's weird, huh? I don't have, block mn, block mn. Okay, how come I don't have the case study? You know, sometimes I might have deleted. Make C, make, okay, it's right here. So here I'm running that pieces of code, and I should be able to get some output. So what I'm doing, okay, let me restart from scratch. Okay, so here I'm making the matrix multiplication code, and let me compile it. So you can see, right, when I compile it, I enable -03, which is a very aggressive optimization. And now I run the code with various different sizes, 32, 10K, 1K, and 2K, right? And let's see what the performance looks like, right? Which some of you already, if you remember, right? So in the very beginning, okay, so here's the execution time, right? So if you have 1K elements, it's about 2 seconds. If you have 2K elements per row, per column, it's going to be 24, right? Which is surpass the projection of your computational complexity. However, if we use the block matrix multiplication algorithm, and let's see how that would perform. Why is it taking so long? Did I do something wrong? Oh, here we go. Okay. Oh, because I additionally run 4K. So here's the thing. This the first one is actually the 32 by 32. It's really fast. And for the 1K by 1K one, it takes only 0.72, and the original one takes 1.97, right? So it's pretty much like a 3 times speed up. And for 2K by 2K, it's actually 4.2 versus 24 here, right? So it's pretty much like a 6 times speed up. And another thing that I think worth noting is that if you compare the performance ratio here and this one, it's actually aligned with the older n cubic code. So which tells you another thing. If we can ignore the factor of caches, then actually computation complexity is correct, right? Without considering the factor of cache misses, computational complexity actually works. So that's why I'm saying computational complexity would work if you give it a perfect world. However, that's not always the case, right? Okay, so I hope this would give you sufficient amount of hints regarding how to address your programming assignment. And for your programming assignment, it's due next Thursday in 7 days. So that's why I kind of like changed the order of the lecture. Otherwise, according to our original schedule, this lecture is supposed to appear in the next Tuesday, which is probably too late for you, right? And in fact, in our assignment, we also tell you you should use tiling, but sometimes you guys just like me to explain that again. So I appreciate that. And originally, we have a reading quiz for due next Tuesday, but I figured out that because that was based on the schedule for the last quarter, and this quarter, if you remember, we start on Thursdays, right? And so that's why our midterm is actually in a different week than the previous quarter. So it will be due on a Thursday after the midterm. However, if you want to start with it right now, I won't prevent you from doing that. And I just uploaded the participation grade on the website that shows you the grade. And there is a reason I don't want to use eLearn because it sometimes generates incorrect mapping between the answers. The student and the real result when I upload it, which is very annoying. Assignment 3 is up, due next Thursday. Programming assignment are perfect link to the lecture. Some of you were thinking about, I got no hints for the second programming assignment. In fact, if you review the slides on lecture 1 and lecture 2, right, I already tell you the solution there. It's just require a little bit of you. So sometimes it's really important. It's not that the teacher didn't tell you, is you never thought about these things can link together, right? So here today, I specifically tells you if you want to get good performance on assignment 3, this is what you want to do. But I would never do that in the future. Okay, and plagiarism ratio. So first of all, I want to state carefully, clearly, if you copy paste code from the website, that's definitely a plagiarism ratio, regardless what kind of license they provide. If you copy the answer from ChatGPT, right? And this time when I designed the second assignment, it took me a third assignment. It took me more time because I did ask ChatGPT and Bart about the answer. Am I sure they don't generate the answer that would meet our performance requirement? So that's why it takes me more time. And the reason why I'm so keen about this is because as someone who worked for a company before, we know how strict are we in asking generative AI to do things. It's very dangerous for a few reasons. First of all, they would collect your user data when you sign the agreement of using their service. If you are working for a company, if you ask generative AI questions, you are leaking your company's secret to another company. Are you aware of that dangerous? So a lot of you were saying that, okay, Copilot is there. Why don't I use it? No, you cannot use it because when you use it, you are also leaking important things and you will get sued. And it's really important for you to practice the skill that without relying on those tools, how can I write in production software? Okay? So that's why I'm so strict about these policies this time, because I found it's really a thing that I need to have you be aware of. All right? But other than that, thanks for coming today, and I will see you next week. Enjoy the rest of your week.